About light. I want to make sure that everyone understands that we're talking about non-mechanical waves. At the very beginning of the waves unit, we discussed the difference between mechanical and non-mechanical. Every wave we've discussed up until this point has been a mechanical wave. What separates non-mechanical waves apart from mechanical waves? Non-mechanical waves do not need a medium. Mechanical waves need a medium. So this is the first wave that we have talked about that does not need a medium. First wave that does not need a medium. Okay. Aside from light, all waves need a medium. The only one that could possibly be up for argument is gravitational waves. If Einstein's right, they totally have a medium. It's space-time. And Einstein doesn't seem to be wrong very often. Alternatively, if quantum mechanics is right, maybe gravitons travel. It's hard to say. But for what we care about, light is the only wave that doesn't require a medium. So what we're going to do from here is we're just going to take a look at the different types of light. So the electromagnetic spectrum, starts with radio waves and ends with gamma waves. Second hour wants me to point out that you're going to want a little bit of space to write examples of them nearby. Okay, so after radio, we go to microwave, then infrared, visible, ultraviolet, X-ray, and then gamma. As we go down this chain, they get higher frequency. As we go up the chain, they get longer wavelength. And also as we go down the chain, they get more energy. Okay, we could take a look at an equation that tells you exactly how much energy they have based on their frequency, but we don't have to, so we're not going to. Okay, so we're going to go through these real quick and just pick out some examples of what they're used for. Radio waves, what are they? Yeah, radio. What else? Telescopes, absolutely. One of the biggest telescopes on the planet, single dish telescope, is Arecibo. And it appears in, anybody know this one? It appears in what James Bond film? GoldenEye. That's a really good guess, yeah. Big radio telescope, Arecibo, appears in GoldenEye. It's the big dish that they're fighting in at the very end. Because that's what you do in James Bond. All right. So radio waves, used for telescopes, used for radio. What else do we use radio waves for? Communications. I'm just going to put that as a large one here. Communications. Sound. Okay. Communications could be cell phones, could be radio, could be GPS satellites, could be your TV broadcasts. Communications is pretty much there, and I'll put telescopes here. All right, next one on our list, microwaves. What do you use microwaves for? So heating or cooking. Oh man, there was a group of kids, I don't know, a few years ago, who they really thought we should do a Hot Pocket lab. I'm really not sure how you would do a Hot Pocket lab. All right, so microwave, aside from cooking, what else are they used for? I'm not talking the appliance in your kitchen. Maybe. Not usually. I mean, that's literally all of these are radiation. Okay, technically you could do that because wireless networks function right in the same spectrum. So turning on a microwave will disrupt the wireless network around the microwave. They can be. So microwaves are also used by communications. Have you ever heard of a shortwave radio? A shortwave radio, well, let's take a look here. If a radio is a long wave radio, then shorter wavelengths would be microwaves. These are actually used for communication. So I can't remember if it was World War I or World War II, but there was a communications officer that reported to his station every day and brought with him his lunch. And he found, depending on where he placed his lunch around his station, he would by lunchtime have either a melted chocolate bar or one that wasn't influenced. And he found that as he placed it closer to the microwave transmitter of his shortwave radio, the chocolate bar was more likely to be melted at lunch. So coming home from duty tour, the guy invented the microwave used for cooking based on his experiences enlisted as a radio communicator, because he found out that microwaves carried enough energy to actually heat food. So microwaves totally can be used for communication, but that's war is actually where our understanding that it could be used for cooking came from. Next up, infrared. What do we use infrared light for? No? I mean, yeah, telescopes, that's heat. Okay, so, all right, so you're saying night vision goggles. All right, so infrared vision, yes, absolutely. I'm going to lump that under heat because that's what you're looking for. Okay? Heat, what else is infrared used for? Say again? Right. I mean, that radiation is heat that you're looking at. Anybody have a Wii at home? Okay, the sensor bar that you put either above or below the TV, it's totally not a sensor bar. It's a pair of infrared lights. You can use candles because they're just heat. So your sensor bar for your Wii, it's not collecting any data. It's just pointing out two little infrared lights that the remote can say, oh, here are the edges. And if you got rid of that thing and, like Will said, put a pair of candles up, they're just infrared sources. They're just heat sources. Your Wii remote might not have as nicely defined edges, but it'll totally track those candles and still stay between them and on your TV. So we could also use this for data transfer. So aside from the Wii remote thing, it's your TV remote. It's your, somebody in second hour said DSs communicate with each other using that. Those didn't communicate to anything ever. Okay. Next up, visible light is used for, I'm going to put seeing. Okay. Ultraviolet. What is ultraviolet used for? You can use it to clean things and sanitize them. Okay, so sanitization. What else can you use UV for? Burning your skin. I'm going to put skin cancer here. I mean, some people go intentionally try to get this stuff, so I don't know. I don't get it. And for most of you, UV radiation is useful for getting your vitamin D for the day. Some of us don't need that because we have weird mutations that allow us to produce our own. No, only Connor and I do. Yep, because he has red hair. Yeah, we've got a weird mutation that allows us to produce our own vitamin D, whereas whereas the rest of you guys had better go outside in the sun and get your own vitamin D. All right. Let's see here. So skin cancer, vitamin D, sanitization, X-rays. They're used for medical purposes. You can. though I'm not 100% certain if they actually use X-ray there. I don't actually think they do. I think they use a different version. Yeah. All right. So you're at the dentist. They're X-raying your teeth. Where's the dental technician stand? Behind a wall. Because X-rays cause cancer. Right. Which is why the dental technician who would have repeated exposure to this needs to not be there. Okay? So your body can process a certain amount of radiation every year without any problems. When we're talking about someone who's going to be introduced to that multiple times a day, your body can't process that much. So they need to stand somewhere not by the radiation, so they don't incur that kind of risk. Gamma radiation, what's this used for? Death rays. Okay. I'm going to put causing cancer. I'm also going to put fighting cancer. Because if we are talking about radiation therapy uses X-ray radiation. Sorry, not X-ray radiation. It's a mix of X and gamma radiation. We need to put the Hulk on there. So gamma radiation also hitting the Hulk. Okay. So few myths I want to talk about here. So how many of you have heard that talking on the cell phone too much can cause cancer? Yes? All right. Ladies, how many of you have heard that you shouldn't store your cell phone here because it presents dangers? Guys, how many of you have heard you shouldn't store your cell phone in your front pocket because it can cause cancer? Okay? None of those things are true. Not a one of them. And I can prove to you that they aren't true. First of all, we could go take a look at some studies that have been done. But second, we could just look at which one of these has caused cancer. Yeah, the higher frequency, UV, X-ray, gamma. More notably than higher frequency, they're higher energy. In order to mutate cells, the radiation needs enough energy to actually cause changes in the cell's makeup, in your DNA. Visible light, infrared, microwave, radio, these don't have enough energy to do that. If any of these, aside from these three, were going to cause cancer, the next one that would be most likely, the light we use to see. That would be the next most dangerous out of this list. And you know what doesn't seem to be causing us cancer? Turning on the light. I mean, that fluorescent bulb is not more dangerous than these. Okay? Radio waves. This is you and standing in front of a microwave. These ones are the lowest energy. They are the least likely to be able to cause any kind of cell mutation out of the entire set. Sounds like a stupid game. No? Okay. So out of any of these, UV, X-ray, gamma radiations are the only ones that are actually dangerous because they're the only ones that can cause cancer. I mean, obviously, if you get enough microwave radiation, enough infrared radiation, you could literally just cook. It's called standing too close to a fire. But that's not cancer. That's what we call being on fire. So know the difference. Yes. It makes more fire. All right, moving down our list here. So after talking about the different types of radiation, our next topic that we've got to take a look at is really more of a historical perspective on things. And that's jumping back to the 1800s. If you existed in the 1800s and you were a physicist or someone involved in the scientific community, you would probably have a strong opinion about whether light was a wave or a particle. And no one really agreed, and there were very heated debates between physicists about this. I mean, probably not quite as heated as Tycho would have gotten about anything, but heated debates. And some of the evidence for light as a wave, we've already talked about. as a wave. First of all, light reflects, other waves reflect. We've already talked about reflection. So I'm just going to put down here reflection. Okay. The next one that I'm going to put down is diffraction. Diffraction is the changing of the direction of a wave as it passes an edge. The changing of the direction of a wave as it passes an edge. One of the best examples for this is harbors. So if we're at the edge of the ocean, we've got waves coming in from the ocean. And what are we going to do to make sure the harbor isn't constantly battered by waves from the ocean? Sandbars. We build some kind of wave break. If waves didn't diffract, what this would mean would be now that all these waves strike this barrier, and then some waves make it through in this concentrated beam of waves that only strikes something. Well, that looks ridiculous. That's not how these things work. When we see waves come through a wave break, we see them propagate out in all directions. We do. So the waves don't just travel in this nice beam and just berate one guy's boat somewhere in the harbor. They actually travel out in much smaller amounts. So the total amount of energy here largely dashes itself upon the sandbar, but some amount that makes it through here then fans out through the rest of the harbor, propagating in 180 degrees. Okay? So if light can do this thing where it passes an edge and bends, passes an edge and bends, I should say there are kind of angles here that are super quiet, but they're not completely silent there. And when I mean quiet or silent, I mean there's no waves. Okay. There are some spaces that it's not doing a whole lot, but if light can do this, then light is a wave. So we'll show you light doing this. So that's diffraction. Questions about diffraction? Cool. Then we get on to our last one, which is refraction. Refraction is the bending of a wave as it enters a new medium. The bending of a wave, yes, as it enters a new medium. This occurs because the wave speed in the different mediums has a different value. When the wave speed is lower, the wave bends towards the normal. When entering a medium with lower wave speed, the wave bends towards the normal. Okay. All right. So what's that look like? Oh, dark matter, dark energy. It's not. It's not. All right. Questions as to what any of these variables in this equation for Snell's law represent. Again, theta 1 is your incident angle. Theta 2 is the angle coming into the new medium. V1 is the speed of light in your first medium, usually air. V2 is your speed of light in the new medium. And we can express those as indices of refraction, N2 over N1, which are calculated as speed of light and speed of light in the substance you're interested in. We good? Speed of light in vacuum, 3 times 10 to the 8th meters per second. Let's go ahead and take a look at how this actually works with the example we have here. So we said that our sine of angle 1 was 55 degrees, divided by sine, and our angle 2 was 37 degrees. that means that we can figure out the speed of light in water, and we can figure out the index of refraction of water based on this equation, so V1. The speed of light in air is basically the same thing as it is in a vacuum. It's like 2.99 compared to 2.98 times 10 to the 8th meters per second. So for our levels of precision, it's the same thing. So 3 times 10 to the 8th meters per second divided by V. Okay, I'm going to go ahead and find these values, do a little algebra. So sine of 55 divided by sine of 37. Oops. I get 1.36, and I'll apply that up. 3 times 10 to the 8th divided by that value, I get 2.2 times 10 to the 8th meters per second. Is equal to 2.2 times 10 to the 8th meters per second, which is about right for water. That's pretty good, actually. Okay. If I then want to know the n value for water, all I've got to do is take C, 3 times 10 to the 8th, divided by V, 2.2 times 10 to the 8th, and divide, and I get my n value. So 3 divided by 2.2, I get 1.36. It is an index of refraction. It is the ratio of the speed of light in a vacuum to the speed of light in whatever substance you're interested in. Okay. Why didn't I just do this to here? Because I wanted to take the pit stop and find the actual speed of light in the water. Okay. Let's see here. Demos that I've done up here that I wanted to show you. No, I got them all. All right. Questions about light as a wave. Okay. So 1800s again. Light is a wave. That means that light needs to have something that every other wave has. Light needs a medium. Unfortunately, that means that light needs something that exists in a vacuum, because in the 1800s, while we haven't been to space, we do understand that we can make a vacuum chamber and light travels straight through it without any issues. So that made people theorize a substance called the ether. The ether was a proposed substance through which light traveled. It was the medium for light. The proposed medium for light. Now, the ether was supposed to be a substance that permeated the entire universe and interacted only with light. So you're supposed to try and find something that's invisible, intangible, and interacts only with the substance that you're trying to explain it travels through. Okay, this sounds made up. And a couple of scientists by the name of Michelson and Morley figured out a way that they could actually test and see if it existed. So this is the Michelson-Morley experiment. And Morley experiment. So what they did was they designed what we call an interferometer. That word's kind of cool because we actually just used one a few years ago to detect gravitational waves. It's the same idea, same setup, just not using mirrors, using some telescope techniques. And the interferometer took a beam of light and had it hit a slightly perforated mirror. That beam of light then went up to a solid mirror, back down through that mirror to a detector. Meanwhile, the second portion of that light came off, hit off a mirror, came back, bounced down, and reached the same detector. What this then did was this created two beams of light from the same original beam, one traveling a path that is mostly perpendicular to the original path, and one following a path that is mostly parallel to the original path. This was significant because based on the definition of what the ether should be, Earth should simply travel through the ether, both in terms of its orbit around the sun and in terms of its daily axial rotation. And if the light beam that traveled in this direction arrived at a different time than the one that moved perpendicular, that would be because the one moving parallel to Earth moved faster through the ether because Earth basically boosted its speed. Okay? Whereas the one that traveled perpendicularly wouldn't experience that boost because Earth was not traveling in the same dimension as it. So if these times appear different, then the ether's presence would be confirmed. However, what do you want to guess happened? They're the exact same. So this is a diagram of the interferometer, and they showed that the ether was not present using this experiment. Showed the ether was not present. Okay, great. So we've got evidence that light is a wave, but we've got no medium for light. And this is one of the big reasons that people said, well, clearly light is a particle. Besides it needing a medium if light is a wave, we've also got evidence that light is a particle. Light is a particle. The primary evidence for light as a particle comes from what we know as the photoelectric effect. Photoelectric effect. The idea being that if you take a piece of gold and you shine a blue laser on it, electrons come flying off. And if you hook this up to a voltmeter, you actually get a current. Okay? So blue light causes current as electrons are removed from the gold. Okay? Because an electron has mass, that means that it has momentum now. So in order to conserve momentum, that means that a light beam or a light particle must have mass. Otherwise, you violate conservation of momentum. So light must be a particle to conserve momentum. Okay. Okay. So we've got evidence that light is a wave. We've got evidence that light is a particle. We've got a demonstration that there's no medium for light as a wave because there is no ether. So how quick would you guess that it takes them to turn out a solution to this? Okay, 100 years puts them into our realm right now because this was done in like 1904. Yeah, Einstein's the next one can come up with this. So I don't know about you guys, but I'm sitting here and said, oh, we've got light as a wave, we've got some proof. We've got light as a particle, we got some proof. So it's both, right? It seems pretty easy to put together. Yeah, evidently not, because no one gave reason and gave explanation for that until Einstein. So Einstein, in special relativity, explains that light is both a wave and a particle. Is both a wave and a particle. That seems really obvious to me. I mean, yeah? Yep. But I mean, they had the evidence sitting right there. In the same way, we've got it written right there. I don't know. So that particle is called a photon. Particle is a photon. A photon is simply a packet of energy that moves like a particle. A packet of energy that moves like a particle. It also moves in a transverse waves pattern. Photons move in transverse wave patterns. We can prove that they move in transverse wave patterns using a demonstration called polarization. All right. This says that light moves as a transverse wave, and that not all beams are always in the exact same orientation. Light moves as a transverse wave. And how many of you have ever had polarized sunglasses? Yes? What are they useful for? Seeing through water, because you remove the glare, because the glare off of water is polarized. So a polarized lens kind of looks like this. Kind of just looks like a sunglass lens, right? Nothing terribly exciting. So this lens has a whole bunch of vertical strips in it that block any light trying to go like this. Any light going like this makes it through. So if I've got two of them, I doubly make sure that's the case. But if I turn one of them 90 degrees, it now blocks the light that's going perpendicular to it. And I can adjust what percentage of light actually goes through based on how much travels through each one. Also cool, anybody who's got a Droid phone, light from your screen is polarized. Apple phones, yours is not polarized. I have no idea why. See you guys tomorrow. Yeah. See that?
Wait, that's what I was just figured it out. Yeah. I mean, granted, I didn't have the information, but like,
No, I'm just not like, why is it turning off? I gotta go right. I would have been really worried if I didn't know about polarized lenses. I would have been really worried. I was for a moment. And then I realized, wait a minute.
I know this. This is supposed to happen.